Okay, on the board I have a plus b cubed, and I want to expand this. Now we can use our FOIL method. What do I mean by that? So for example, I can do this. I have a A and a B. So basically what I'm doing first is that I am expanding a plus b squared. And then I'll be multiplying whatever I have over here by a plus b. So what does this equal? Well, first we choose an a and an a, so this will be a squared. This from here, we're producing an AB term, right? So a times b is ab, this will be ab, and b squared. And after this, you'll just add your result together, and at the end you get a squared plus 2ab plus b squared. And after that, you can do the same thing here. I leave it to you as an exercise, and then you'll end up with your final answer right here. So although this is one way to do this, what if instead of a 3, I have a larger number? What if I have, for example, n, right? I want to expand a plus b to the power of n. And this is where the binomial theorem will come in. And this will be something you'll be learning probably during your pre-IB2 years, or maybe at the start of IB1 as a review. But the binomial theorem will allow you to expand anything like a plus b to the power of anything pretty quickly, much quicker than the FOIL method, where you calculate the products of coefficients, and this could result in a lot of error. But however, first we should intuitively understand the binomial theorem. Why does the binomial theorem work? And in order to motivate this intuition, let's first start at our a plus b cubed again. Okay, so here we first ask ourselves what terms can possibly be produced. So first, if you've done your multiplication, you probably noticed that you got an a cubed term, right? A cubed. And then there's a coefficient in front, so I just want to find this coefficient. Well, what is this coefficient? Actually, for clarity, I'll write it as this. So this is basically the product of a plus b 3 times. And then I want to find the coefficient of a cubed, right? So how do I do this? Well, in order to produce this term, so how do I even produce this term? Well, to get this term, you grab an a right here, right? And then you multiply by this a right here, and then you multiply by this a. So basically, from each of the a plus b's, the 3a plus b, if I want to get a cubed, I have to choose a from all of them. And I just basically ask myself how many ways I can do that. Well, there's only one way, which is just to choose a from all of them. So therefore, this is why the coefficient of a cubed is 1. And next, you'll probably notice that there's a squared times b term. So if I want to get a squared times b, how do I do this? Well, there are actually 3 ways to do this. So I think I'll pull this out right here. Okay. Okay, so how do I do this? So I can grab an a right here, right? So I pulled a out here, an a down here, and a down here. I mean a b down here, yeah. So this will be a times a times b, right? And this will get us a squared times b. Well, this is not the only way to do this. Actually, I can also do this. I can actually pull a b from the second product. So it becomes ABA. And a times b times a is also a squared times b. And the third way to do this is b times a times a. And you notice that there are 3 ways to do this. Therefore, the coefficient of this is 3. And if you look into this more, well, this is basically the numbers of ways I can rearrange 2 A's and B's. So there are 3 ways to rearrange this. And if I want to continue, well, the coefficient of A squared of A times B squared is also 3. Because there are 3 ways to rearrange a sequence of 1A and 2 B's. So that would be ABB, BAB, and BBA. And finally, there's one way to rearrange a sequence of 3 B's, right? If you have 3 B's in a row, the only way to rearrange 3 B's in a row is just B, B, and B. There's no other way to do this because all the B's are indistinguishable. They are treated as the same. Okay, so now we have this as our example. Now what if I want to explore higher powers? All right, what if I want to do, instead of a plus b cubed, I want to do a plus b to the power of n. Okay, well this is actually the same logic as our a plus b cubed, right? So for a plus b cubed, well, we ask ourselves, what terms can we produce? Well, we can produce an a cubed term because a times a is a cubed. That's possible. An a squared b and an ab squared as well as b cubed term. Right here, we can produce an a to the power n, right? Following our logic on a plus b cubed. We just have to ask ourselves how many ways are there to do this? Like how many ways are there to rearrange a sequence of n a's? Well, there's only one way to do this, which is just a bunch of a's, depending on your value of n. One way. Now, I want to find the coefficient of a to the power n minus 1 times b. So what does this mean? So I have n minus 1 a's, so a bunch of, let's say a's. So there are n minus 1 of these, right? And then a b. So how many ways are to rearrange this? So there are n letters in total. Yeah, so if we treat all the a's as distinct, well, there will be n factorial ways to rearrange this, right? But however, like not all the a's are distinct. Therefore, we have to divide by the number of ways to rearrange the a's, like if they were distinct, right? So that would be n minus 1 factorial. Actually, another way to think of this is that if you have like n slots, so you have n of these spaces. Like one way to look at this, I guess, is how many ways are there to put b, right? How many ways are there to choose spots for b? Well, this is just n choose one way, right? We will write it like this. Yeah, so this means that, so let's say right here, yeah, okay. N choose k. So this means, like if you have n objects, how many ways are there to choose k of them, right? And this equals, yeah, so for more background, I guess. It equals this. And notice that we divide by k factorial because like the k's objects, they are indistinguishable, right? So without the k factorial, like if we don't divide by k factorial, this is just the number of ways. So there are k objects, yeah. So this will just be the number of ways to like rearrange the k objects. But because the order doesn't matter, this is why we divide by k factorial. So there's that. Okay, next is we want to find the coefficient of this term, right? Now the only difference here is that, well, there's actually two b's right now. So instead of n minus 1 a's, there will be n minus 2 a's. And there's still n slots, there's still n letters in total. We're just gonna ask ourselves how many ways are there to place b's, because after we place the b's, like the a's automatically go to their spots. Well, there's n choose 2 ways to put down the b's, so therefore this is the coefficient. So now let's say we continue on and on. And now finally we get to b to the n. Well, there's only one way to rearrange a sequence of b's, of n b's. This is just all b's in a row, so therefore it's 1 right here. And actually, instead of writing a 1 right here, I can write n choose 0 right here. N choose 0 instead. This basically means if we have n objects, how many ways are there to choose nothing? And this is just 1, because choosing nothing is actually one way. We just do nothing. And we can write here, instead of 1, we'll write n choose n. So if we have n objects, how many ways are there to choose n? We just choose all of them, right? So there's one way. Okay, so based on all our intuition right here, we have this formula right here. However, of course, we should probably prove this using proof techniques like mathematical proof techniques. And right here, we can use a technique called induction. And induction will also be something you'll learn in IB, like first year of IB. For me, I learned it towards the end of the year of IB1. So what is induction exactly? How does induction work? So first, you need something called a base case. And this will just be so let's say you have a row of dominoes, right? So this is one analogy that mathematicians make. Induction basically works like this. So if you knock down one domino, right, the rest of the dominoes falls as well. And the base case is just basically what starts this domino falling process. And in mathematics, so you first assume that this holds. So let's say this holds for some integers. So for any integer n, right? We first assume this. And then we show that it also works for n plus 1. And the reason why this works is because, let's say we have our base case. Our base case is n equals 1, right, for positive integers n. So because it works so we show that if it works for n, it works for n plus 1, right? And we have our base case, which is 1. This is our starting point. Now, because this works for n equals 1, therefore it works for n equals 2. And because it works for n equals 2, therefore it works for n equals 3. And because it works for n equals 3, therefore it works for n equals 4. And it goes so on. And at the end, we end up getting all of our integers right here. So yeah, we'll prove this using induction. So let's say, so this is our base case, right? Our base case will be n equals 1. So if we substitute 1 in here, we get a plus b. And if we substitute 1 right here, well, this will just become 1 choose 0 to the power a to 1 plus n choose n. So that'll be 1 choose 1, b to 1. And if you work out this side, well, 1 choose 0, you end up getting 1. This will equal 1. And this will also equal 1. So therefore at the end you get a plus b equals a plus b. Yeah, so our formula works for n equals 1. So now we are going to assume that this is true, right? It works for, let's say n equals k, right? So we are going to assume that, we're going to assume a plus b to the power of k equals, so what we have here, okay, so we are assuming this. Now we want to show that it also works for k plus 1. And one good technique for induction, I guess, is if you substitute k plus 1, so n equals k plus 1 in here, the reason why we do this is for us to have a better idea of what to expect as a result. Because soon we're going to be doing this, right? So we want to show that it works for a plus b to k to the power of k plus 1. And this will equal, so this equals this, right? So afterwards, we're going to use an assumption. This is also known as inductive hypothesis, I believe. So we're gonna substitute a plus b to the power k in here. So after doing this, we will be multiplying everything out. And yeah, notice that the reason why we should substitute n equals k plus 1 here. So we know what we will get. And this will guide us into what we should do next. So for example, after we expand this everything out, it will help us, it will guide us into how to group these terms together. So what does this expand into? So first we'll be multiplying everything here by a, and afterwards we will be multiplying everything here by b. So it becomes a choose 0. Okay, now we're going to multiply everything here by b. So oh yeah, a choose 1. Okay, after all this, we can now group the terms together. So notice that there's a to the power k times b here, and there's a to the power k times b over here. And also there's this term right here, and there should be one over here as well. Yeah, so it's this one right here, right? So we're going to basically be grouping everything together, and at the end we get this result right here: k choose 0, a k plus 1. What does this become? So this will become k choose 1. So we're going to factor out all the variables after it. We're going to leave the coefficients right here, and we'll see in a moment why we want to do that. Because we will be applying a combinatorial identity right here. Yes, this. Looks seems small, I think. Yeah. So we want to find this one right here and this one right here. Yeah, so this will be k choose 2 plus k choose 1. So what will be the term right here? It will be a to the power k minus 1 b squared. Okay, we're going to continue over. And finally we arrive here, right? And there's only one b to the power k plus 1, but this will be okay. And now we want to figure out what to do with all these sums right here. Like, what does this equal to? This is where we will be applying our combinatorial identity. And this is also known as Pascal's identity. Pascal identity. So looking over here, I believe that it is n choose k plus n choose k minus 1 equals n plus 1 choose k. Yeah, based on what I'm seeing right here. Yeah, so this is known as Pascal's identity. And if you want to show that this is true, well, I'd say the most straightforward way to show that this is true is just by algebra. So you're basically just using the fact that n choose k equals n factorial over k factorial times n minus k factorial. And then after you do all of this, and then you add the fractions up together, you can see that this side will equals this side. However, there are also other ways to do this. Well, you can search up committee forming arguments, right? So you can look at this as a committee of, so you have a total of n people right here, and you're basically just choosing people to form a committee. So this is another way to do this. But for now, I say, yeah, the most straightforward way is just to expand both sides using this fact right here. Okay, so after this fact right here, so we have k choose 0 right here. So what does this become? After applying Pascal's identity, this will become k plus 1 choose 1. Yeah, and we still have this right here. K plus 1 choose 2. Choose k. Although we're not completely done, because like you realize that k plus 1 is all right here, but this is still k. Well, this is okay because k choose 0 equals k plus 1 choose 0, right? These are equal. And same thing, we can do the same right here. K choose k is k plus 1 choose k plus 1. You notice that these two are also equal. So yeah, after just substituting these in here, we have proven binomial theorem using induction. And this is a more rigorous way of demonstrating the validity of this formula. So we have first looked at it in an intuitive way, just like writing everything a plus b, right? N copies of these, and choosing a and b, and then multiplying together to form terms. So this is a way of understanding like why this is true. But yeah, based on our proof right here, we can be like more certain about our intuition. So there are also, I guess, problems about binomial theorem. So normally on your IB exams, right, you're not going to, so if you have a, let's say a plus b to a very high power, right, like I say the exams won't be asking you to write down like the full expansion of everything, because that would just be a sort of a time sink, right? That would be a little ridiculous. Instead, they might ask you to find the coefficient of a certain term, right? So what do I mean by that? I don't have, well, I'll just get one in my mind right now. Okay. Okay, let's say you have like this, right? Actually. Okay, let's say you have this, right? To the power 5. It's a very, very huge power. So like if an exam asks you to like expand this entire thing, then yeah, good luck with that. However, an exam might ask you, let's say, find the coefficient. Find the coefficient of x to the 4, right? Okay, but this is like, once again, you're just gonna ask yourself, how can I produce x to the 4? Well, from here, so imagine that this is just 5 copies of 4x squared plus 5. How do I even get x to the 4? Well, I have to choose 4x squared 2 times, so I have to do this, right? I have to do this twice, right? 2 times. And then, because there's 3 more to choose, well, we have to choose 5 for the rest, right? And if you expand this entire thing out, you'll realize that there will be an x to the 4. However, this is not the answer, because this is not the only way to do this, right? Because we have 5 of these, 5 copies of these, and we want to choose 4x squared from 2 of them, we have to ask ourselves how many ways are there to do this, right? And this is just 5 choose 2. So therefore, we can imagine adding 5 choose 2 copies of this. And, well, this is our old friend multiplication right here. 5 choose 2. Therefore, we want to find coefficient. Therefore, it's just a number in front of x to the 4. And we will be expand this thing out, I guess. So 5 choose 2. Well, this is 10. I'll tell you that. But you can use the fact from like previously in the video to further verify this. Yeah, it will be 10. What is 4x squared? And then you square this. Well, this will be 16 x to the 4. And 5 cubed is just 125. Oh, seems like I didn't give myself very nice numbers. Hold up. Yeah, this will not come straight in my head. Okay, you know, for practice, I'll just multiply this out. Okay, so 125 times 10 is 1250. I want to multiply by 16. So there's 0 here, 0 here, 3 up there, 5. Does this look right? Yeah, this looks right. 1250, right? I believe so. 0, 0, 0. Oh wait, is it 20,000? Okay, yeah, that makes sense actually, because 125 times 8 is 1,000. Yeah. Okay, so therefore this equals 20,000 x to the 4. So therefore, our answer will just be 20,000. I say this is a much nicer answer than just to expand this entire thing out. Another problem, I guess, it might ask you, for example, they might give you a coefficient of a certain term, and then you might be asked to find like the power, or maybe one of the terms in here. Like that, I guess that's another type of problem they might ask you, but I don't think I could come up with one right now that will produce nice results. But yeah. So yeah, when in exams during binomial theorem related problems, like you're rarely going to be asked to expand out the entire thing. Usually you're just going to be asked to find like one term, what one term is, or maybe you're going to be asked to find the powers or the things inside the powers and all those things. But just remember, if you don't remember the binomial theorem formula, well, just ask yourself like, what terms could, like if you want to expand a plus b to the n, right, again, right, and you don't remember the formula, well, you just have to ask yourself, well, what's the coefficient of a to n, because this expansion could produce a to n. Well, there's one way to produce a to n, right, or we can write this as n to 0, and then you continue down a to the n minus 1 plus b. And how many ways are there to do this, produce this term? Well, you're just basically choosing n minus 1 copies of a's and 1 b, and there's n choose 1 ways of rearranging this, right? So therefore, it's n choose 1 right here. So as long as you're comfortable with this intuition right here, or understanding exactly like why this formula holds, you don't really need to remember precisely these. Just follow the intuition, like whatever works best for you, your understanding of this formula. So yeah, that's about the binomial theorem. It'll be in the IB exams somewhere. And yeah, have a great day, guys.